The industrial and healthcare IoT edge starts where the real world turns into digital information. Camera imagers, medical imaging and diagnostic sensors, high-voltage electrical converters, and servo position monitors translate the analog data surrounding all of us and send it to networked embedded electronics. Why? Does it turn into a game of digital hot potato until it reaches the cloud? Or does the concept of data gravity flip the script by emphasizing the need for intelligence and adaptive computing inside these devices? Assets like this AGV, this wind turbine, this patient monitor, and this camera can reduce operational expenses by avoiding unnecessary transmission, storage, and processing costs, and by doing so react faster on their own, protect data more securely, and make intelligent decisions safely. These systems all use some combination of what has become a required set of robust IoT technologies, starting with IEC 62443 grade cybersecurity with hardware root of trust, IEC 61508 based functional safety, communication standards spanning from EtherCAT to OPC UA over TSN, embedded vision technologies, control for multi-axis motors, mixed criticality software that balances ease of use and the feature set of Linux with real-time operating system quality determinism, and last but not least, machine learning-based AI. Here's the catch. With this lineup of technologies, you'll need time to integrate them into each product. In order to counteract this reality and be efficient with time and engineering resources, most industrial and healthcare companies focus on creating embedded platforms that can scale from the low to high end of their products and across multiple product lines. Did you know that the number one reason industrial and healthcare customers select Xilinx Zynq SoCs and Versal ACAPs is because Xilinx offers the most scalable embedded portfolio in the industry? The ability to have a common processing architecture to leverage and extend your software investment, along with customized hardware acceleration for individual applications, sets Xilinx apart in industrial and healthcare IoT. Moving beyond the silicon architecture, Xilinx has compiled and curated a comprehensive selection of both in-house developed and ecosystem solutions from the most trusted names as part of our industrial and healthcare IoT solution stack. We've invested ahead so you can leverage our toolkit and accelerate getting your products out to customers. With solutions plus easy-to-use design tools and the most scalable SoCs on the planet that check all the boxes for your next industrial and healthcare IoT design when others simply can't. This is why you can build the most intelligent and adaptive assets with Xilinx.
Ladies and gentlemen, please welcome Xilinx President and CEO, Victor Pang.
Thank you, and good morning, everyone. And I've been with the company for over 10 and a half years, and well, I know many people in the audience. I definitely haven't met the majority of you here. So before I get into my keynote, I thought I'd just take a little bit of time to give you a little bit about myself. I'm not going to go through the typical professional corporate stuff because you can get that off of the corporate bio. So I'm going to talk to you just a little bit about one passion that I've had essentially my entire adult life that's not related to my family or my work. And that passion is long-distance running. Now, the first thing you should know is I'm definitely not a fast runner, right? So from a talent perspective, I'm sort of like maybe an above-average weekend warrior type. But the second thing I'd like you to know is that the first time I ran a marathon, I was 23 years old, just at the goading of some work colleagues, and I was totally unprepared. So it hurt like hell, but somehow I finished, and I was definitely hooked. So after that really painful but enlightening experience, I actually set some goals and I actually trained. What a concept at 23, right? So now it's 35 years later, and I've run over 100 races that are of marathon distance or longer. In fact, my longest distance I did that just about 10 years, and I think 5 days from today I did this, and I was 40 years old. At the time, I ran 100 miles. So the reason why I share this is not to brag, but what I learned from this somewhat irrational personal pursuit of mine is that even starting from very humble beginnings, like this totally naive, didn't know what the hell I was doing 23-year-old, that with some passion and preparation, sustained over a very long period of time, in the end you could actually have some pretty remarkable results. When I was doing ultramarathoning, which I don't do anymore, I'm definitely too old for that, it literally transformed me both physically and mentally. And so I guess another lesson to be learned from that when I reflect back is that if you want to become meaningfully better at something, that really requires transformation, and that transformation is really a journey. So I've been CEO for about 9 months now, and for the first 9+ years at Xilinx, I've had the great fortune to work with some incredibly talented teams at Xilinx, fantastic customers and partners, and really we've been undergoing for the past 10 years a transformation as well at the company level. That's where I'm going to start. In the early days, Xilinx invented the FPGA, and PLDs were really used to prototype some ideas, used in applications where there's a lot of bridging and connectivity, and maybe some peripheral functions. Today, FPGAs are incredibly powerful, incredibly complex systems. And our customers are putting them in mission critical, right in the core of their systems. The vast majority of our customers ship our silicon in their production products. In fact, in the automotive market alone, we have shipped over 55 million units of FPGAs. Clearly, that's all production. So we've really come a long way already since the early days of PLDs and when the FPGA was invented. But as powerful and as complex as the FPGAs are today, we've already moved past FPGAs. In fact, what I would submit to you is Xilinx is not an FPGA company. We have transformed to be a platform company. And we did that transformation to better serve our customers and our partners in this world that's changing at an exponential rate. And we're going to continue to transform as needed to better serve our customers. So, the world, we've talked about this as an industry for a long time. The world truly now is becoming pervasively intelligent and connected. In fact, there are many people in this room that are making that reality happen. And this is during the time that there's tremendous amounts of disruption because of the explosion of data, mostly of it unstructured, many of it now currently being processed to become structured. Because of the emergence of AI, and this is really just emerging, but it really is going to be proliferated across all markets, all applications. And because of the slowing of Moore's law and, of course, the cessation of scaling several generations ago. So in this backdrop of tremendous change, people have to deliver products to market faster than ever, and including with some headwinds, as I said, of the ending of Moore's law. So we believe that if you're going to scale out systems and infrastructure at the world level, you really need systems that are adaptable. And that's because you need this tremendous capability of accelerated performance as well as high bandwidth, and yet need the flexibility to deal with new changing requirements, new standards, and scalability. So much like adaptable species in nature, in the natural world, adaptable systems in the digital world will be the systems that are most resilient and ultimately most sustainable when it's scaled at massive levels. So for all these reasons, the mission of Xilinx today is building the adaptable, intelligent world. Now, we've made significant progress over the last several years, but really this is a multi-decade mission. And we're incredibly excited and dedicated to make this vision happen again for our customers and partners, to not only meet the big challenges of the disruptions and trends I just said, but also to really thrive in that world. Now, in February, shortly after being named CEO, I laid out a new strategy that's comprised of data center first, accelerating our core markets, and adaptive computing. Now, the way to think about this, it's like all three elements are critical. It's like three legs of a stool. It's all important for the integrity of the overall strategy. And I would also add that these are much more interrelated than you actually might think. At the time, we also announced the concept of a whole new product category, Adaptive Compute Acceleration Platform, or ACAP for short. And that's a key part of our strategy, particularly the adaptive computing element. I also shared with you at a very high level an internal development project we called Everest, which is the industry's first 7-nanometer ACAP, which later today I'm going to share much more about. So we've made a lot of good progress already since February. You know, we acquired a really innovative and talented company called DeFi and machine learning. I think in the quarterly earnings announcement we had last July, of course now we're currently in the quiet period, but we announced very broad strength in all core markets. So you can see we're progressing already in that short time frame. But today I think you'll understand that we make much more significant progress on this strategy, and we're really, really excited about that. So we've gone through this transformation from devices to platforms through innovating. This is not just about doing the same thing over and over again. This is about creating several new categories of products along the way. And really the first one is when we created the Zinc product where we integrated a full, complete, multi-core ARM SoC together with an FPGA. But we've gone well beyond that, and today our customers are innovating and building new applications across many product portfolios, but tremendous traction on 16-nanometer products with the Kintex and Vertex UltraScale Plus, the MPSoC, which is a second-generation Zinc product, and the RF SoC, which really builds on top of the MPSoC and adds really advanced ADCs and DACs for applications like 5G networks, DOCSIS cable modems, and so forth. So today, our customers are already building very powerful systems on our adaptable systems, 5G infrastructure, as I mentioned, smart, safe cars, factories, other communications infrastructure. So while the silicon is really foundational, a platform is not just about hardware, it's also about software. So we've also been moving to delivering a much broader set of software development tools, not just tools that our traditional hardware developers has always used, the Vivado tool suite, but we built on top of that higher levels of design abstraction with our SDXL, SDSoC, and so forth. And now we're going way beyond that. We're providing optimized libraries, middleware, of course, runtime, in some cases interfacing all the way to industry standard frameworks. So it's this complete platform that you as developers really utilize to bring forth your innovative products and applications. And increasingly, as I said, because of the slowdown of Moore's law and the incredible performance and bandwidth that you require, increasingly you're targeting platforms that have some form of acceleration in it. And increasingly, as I said, that major trend of the emergence of AI, you're also integrating some kind of neural network, in some cases multiple neural networks, as part of the application. So what you really need to do is now a very complex problem that demands high performance as well as in many cases low latency. So I want to share you one really important value add that not everybody fully understands about all our programmable products. And this does include programmable products, of course, that are based on FPGAs, certainly, and where we're going with ACAP. So you as developers need to accelerate your entire application. There are a lot of companies today and startups that are focused only on machine learning, and they're touting how great they are at accelerating that portion of it, but that's only part of the whole application. There's very few applications where all of the execution time is executing in a network for, in this case, by the way, I'm talking about inference. And we already talked about if you run soft on a CPU, you're not going to have the performance that you need. So if you look at what you would get if you just married, say, an ASIC or some ASSP that's targeted for machine learning with the CPU, you will get a reduction in the application latency. But if you contrast what we could do, since we are so adaptable and flexible, we could optimize not only machine learning and also many different networks. We accelerate the other portions of the application that aren't related to machine learning. So again, this latency is actually what the customer experiences. This is the thing that will overall determine the throughput and the TCO of an accelerated data center. Now, you could also say, well, an ASIC could be designed to accelerate an entire application. Well, that's true. But by definition, an ASIC will only be able to accelerate a very small and fixed set of applications and a small and fixed set of DNNs. And that's in contrast to what we could do, because again, you can change our platform fundamentally at the architectural level. And again, there's this term of domain-specific architectures, and the technical community is getting a better usage and understanding. And what that just refers to is the way that we're going to get the mammoth amounts of performance that we need going forward without the benefit of Moore's law or traditional architectures is by narrowing the domain set to a certain set of problems and then having an architecture that's optimized for just that class of problems. The unique thing about our platform is it's so adaptable. You can implement many different domain-specific architectures, or DSAs for short, on top of our same piece of physical silicon. And another really key value add that isn't fully understood is because of this flexibility and adaptability, we let you innovate faster, much faster, than if you relied on silicon design cycles. So this is just an example taking AI, for instance, because that, as we said, it's the early days. We all know there's literally an exponential rise in the publishing of AI research papers. And also the time between someone publishes a research paper to when it's deployed in products is shrinking dramatically. And the reason for that is because people are experimenting. Truthfully, there's not a one-size-fits-all at whatsoever in this space. So people are having to develop new models, they're optimizing those models, and they quickly deploy it, and then they repeat. And you contrast that to a silicon design cycle, which at minimum takes 18 to 24 months. And if it's a really big architectural change and it's a very advanced process node, it's longer than that. So if you again, use our very flexible platforms, you can iterate at this fast rate. You can get many more releases out into marketplace than if you're tied and have a dependency to a fixed function chip. In fact, at best what happens if you do that is the speed at which your architecture or your next release to add new capability, new performance, that becomes quantized as silicon development cycles. So even if you're a pipeline, you're sort of looking at, year plus. And in the worst case, you completely miss the market window. So I want to give you an example of that more specifically. So I talked about machine learning, inference, and DSAs, domain-specific architecture. We have technology we call XDNN, and this is to exactly accelerate. It's an overlay architecture, or a DSA, that accelerates CNN. So our customers don't have to do that kind of work. They could operate using this XDNN. We had a version 2 of that released about 6 months ago. We're just on the cusp of releasing our version 3. And on the exact same 16 nanometer FPGA platform, we have increased the performance of our version 3 XDNN inference performance by 1.7x. Not only that, but we reduced the latency to 1/3, so a 67% reduction on latency while we've nearly doubled the inference throughput performance. And that gets implemented in exactly the same 16 nanometer silicon. So that's demonstrating what I'm talking about and how you can quickly innovate. Okay, so I've talked a lot about how what's unique about us is we could accelerate the entire application. We could also do fast iterations and optimization and deployment to the marketplace. I've done this all sort of at a conceptual level. What I'd like to do now is have a customer come up and talk about what they're doing. And Salil Rajay, who's going to speak to you just after my talk, he's going to cover a lot more about the customers that are doing application acceleration that includes embedded AI, embedded machine learning. This first customer I'm going to have join me on stage, they actually don't have embedded AI, but again, it speaks to the fact that we accelerate applications, including applications that don't have machine learning in it. So 4 years ago, Amazon acquired a company called Twitch. I don't know how many of you are familiar with that, and if you're not, you can think of Twitch as an online network for gaming and esports. And this is a massive market. I don't know, again, if you're all young teenagers, you would all know. You'd be probably using it. It was recently estimated that the viewing audience for esports alone is going to be about 300 million by 2022, which is essentially about the same viewership of NFL football. So they've been growing at an incredible rate. So the challenge that Twitch had was find a way to reduce their operating costs without compromising the viewing experience that they have, so very high resolution. And they wanted to do this because at the same time that, again, they're scaling up because their viewership is rocketing. So I'm delighted to invite Dr. Yoshida Shen on stage to tell us how Twitch accomplished this. So please give a warm welcome to Dr. Shen.
Hello, Victor.
Hi, nice to have you. Please come up.
All right, thank you. At Twitch, we love games. We also love new technologies. I think we made two major contributions to the broadcast industry. First of all, we greatly reduced the barrier of entry to do live broadcast. Anyone has a computer and home internet can do live broadcast. Secondly, with our technology, we create a new paradigm of doing broadcast. And our technology allows interaction between broadcast and audience. Typically, audience may comment about the game through the chat messages, and the broadcaster is expected to answer these chat messages in a timely manner.
So let's talk about how you meet such a demand of real time. And again, your viewership is skyrocketing. Tell us about what your challenges are there.
Yeah, sure. The viewing experience at Twitch that we deliver to our end user is immersive and interactive. It's all depends on high video quality, namely 1080p 60 at 6 megabits per second. We also build data centers around the world to support our peak demand. To just give you a sense of the size of our service, last spring, our peak demand was about 3 million concurrent viewers.
Well, that's really amazing. That's an incredible bandwidth, 18 terabits per second. So tell me what you did in terms of looking for a solution to meeting that kind of demand.
Yeah, 18 terabit is indeed a lot of traffic to provision, and it's very expensive because we pay for every bit that we ship to our customers. Actually, 18 terabits is equivalent to the peak live streaming traffic during the World Cup in the last summer. So therefore, my team was asked to do something that the industry hasn't done before. We have established our design goal as to reduce the bit rate by at least 25% while still maintain the broadcast quality. And to support live streaming, of course, everything must happen in real time, meaning 60 frames per second.
So that means you really need to find a codec that doesn't even exist. You're looking for the next generation codec today. And I know our teams work together on finding that solution, but maybe you could share how you finally arrived at VP9 and what we went through to reach that conclusion.
Yeah, that's a really good question, Victor. So different from linear TV, our content at Twitch, our content is consumed on a wide variety of client platforms. For example, different kind of browsers, Chrome, Firefox, and many Android devices. And VP9 is the most widely supported next-generation video format. And it's also the only video compression technology that we can put into production and still hit our bitrate saving goals. On the other hand, although VP9 can save our traffic, encoding VP9 actually requires a lot of computation power. So to do this, we look at CPU and hardware accelerators. So CPU will be the easiest solution, as you can imagine. But remember, our goal is to hit 60 frames per second. We found in our implementation that even on a high-end CPU, we can only do 4 frames per second, not even close to 60. Also, there are no ASIC or GPU solution even for us to evaluate. And thanks to Xilinx and AWS F1 server product, that we are able to build our solution that can achieve 120 frames per second on a single FPGA.
That's amazing. 30x higher performance than running soft codec on a high-end Xeon CPU. So that's really amazing. What has this meant for the Twitch community and Twitch as a company?
So thanks to our ability that we can innovate fast with FPGA, Twitch is the industry's first deployment of VP9 live streaming at broadcast quality. And we are very pleased with this result and would like to share with the tech community. And more importantly, we strongly recommend the entire streaming industry to seriously looking at VP9, FPGA, and AWS F1. And that's the reason I'm here.
Well, thank you so much. Thank you. Congratulations on amazing results.
Well, thank you very much.
Look forward to future innovation. Thank you. So that gives you a sense of why people are moving to accelerated computing, right? Okay, so I'm going to switch gears now, and I mentioned that when I announced the strategy, I talked about this whole new product category, right? And I just want to be clear that an ACAP is not an FPGA. Remember, that stands for Adaptive Compute Acceleration Platform. It's the next quantum leap in enabling the adaptable, intelligent systems and products in the world. What they are they're very scalable, highly integrated, heterogeneous compute platforms in and of themselves. And they're both hardware programmable, but also software programmable. And they should be supported in such a way that you don't require the hardware expertise to take advantage of the ability to customize the hardware, and in fact, on the fly. So I'm going to walk through ACAP in a little more detail, remember, as a product category, and then I'll share the latest update on where we are at what was called Everest. Okay, so breaking it down, the first A in ACAP stands for adaptive. And as I just walked you through, I think this is a really unique value add for these adaptive platforms in that we could accelerate broad range of applications, including video, no machine learning. We could accelerate machine learning of many different networks and applications that have multiple different types of networks. The key here again is that the customer or the developer can leverage the fact that you can implement virtual domain-specific architectures on a fixed piece of silicon in milliseconds. And remember, this is not just at boot time, but you could do this while it's actively running. Then the second portion, compute acceleration. Again, it's totally set up with the fact that with the end of Moore's law, with the nature of these new workloads are generally more parallel in nature, you really need a diversity of execution engines. So ACAPs will have SoCs on them. Oftentimes there'll be multi-core SoCs. They will also have very advanced programmable distributed DSP engines integrated together with programmable fabric and interconnect, so logic and interconnect. And that's used for the most general and the most customizable kinds of accelerators and kernels. And lastly, a lot of times you can integrate more of these multi-core RAID architectures, but ultimately, again, that our view is in ACAP that distinguishes from some other multi-core architecture is that it will have some degree of hardware programmability, even though you can program it without understanding the hardware in detail. And finally, platform. Again, this is all about platforms. People can't do point solutions anymore. You're not going to implement an ASIC. The economics doesn't justify that for anything at scale. So a platform is made of both that very powerful hardware that I discussed. Right? It's a heterogeneous, integrated compute environment in and of itself, a microcosm of that. But it's also the software development layer. And so ACAPs must be supported for everything you as developers from a software background would expect. So IDEs, optimized libraries, middleware, an ecosystem, and interfaces to standard frameworks where that's applicable. So because of the scalability, this adaptability to deliver both high performance as well as low latency over a very wide range of applications, including machine learning, we see ACAPs becoming proliferated across multiple markets over time. So it's not just for the data center, it's going to be in edge applications, it's going to be in endpoint applications. Truly, it can go end to end. So the big news is we're going to now introduce what internally we had called Everest, and today we're introducing the Versal ACAP, 7 nanometer, industry's very first ACAP. Okay, so the name Versal is based on the attributes of versatility and universality. We developed it to empower every hardware and software developer to use this platform to be able to take advantage of innovation at the pace of this exponentially changing world as we move towards connected and pervasive intelligence. So this lets everybody differentiate, again, whether you're in the cloud or at the edge or the endpoint, and get the benefit of effectively like customized silicon without doing customized silicon. In fact, for those of you software developers out there that don't have hardware design experience, in fact, don't have any interest or certainly any time to do that, you will be able to use and target this very powerful platform. And of course, the benefit that this provides customers and developers is that they can meet the needs of these new workloads and also have tremendous amounts of scalability, protecting their R&D investments because, again, ACAP, the Versal family, is extremely scalable. In fact, we made it scalable as well as extensible so we could address all the multiple markets that you know that Xilinx serves. And so we're going to have several subfamilies, which we call series. And the first series we're going to get out of the 6 that we currently have planned is the AI Core series and the Prime series. And I'll talk about those first, and then I'll talk about some of the other ones that will follow up. And again, this is truly unique to have one product family that could actually span from endpoint to the edge and to the cloud and across multiple markets. So The Prime series, this is a very good mid-range product with a sweet spot that support many different use cases, but particularly those that have a lot of connectivity requirements and wants to do what I would sort of call inline acceleration. And it supports multiple marketplaces because, again, it's a very sweet spot general core basis for the Versal family. Now, the AI Core series, this is really giving you incredible performance in AI inference. Remember I talked about how ACAPS as a product category will have some of these multi-core hardware software programmable engines. So Versal, we're introducing for the first time a new architecture that we call the AI engine. And this is an arrayed programmable, hardware and software programmable processor array, and it really will give factors more performance versus anything in terms of machine learning inference with not only the performance but very low latency, which is really important. And we match this processing capability with very high bandwidth to an incredible amount of on-chip distributed memory, which oftentimes, again, is what limits the actual performance for the application, as well as very high bandwidth to the off-chip memory, and also very high serial bandwidth through very high performance SerDes. Now, common to all the families, much like I said, the overall product category, there's some key elements that every series in the Versal family will have, and that is a whole new platform management control function that enables more of a software-centric way to control configuration as well as other key functions. It also controls more pervasive kinds of functionality like security, power management, and so forth. That's one. The second thing is, again, the next generation, very adaptable hardware that has distributed DSP engines that are hardware programmable, distributed logic, as well as interconnect that's all hardware programmable. And this enables people to create very customized accelerated kernels or data movement engines or control engines or any combination of those. So that's the most flexible, adaptable part of the compute capability. And then lastly, again, I shouldn't say lastly, there's also the multi-core ARM SoC. For Versal, the SoC will have dual ARM A72s as well as dual ARM R5s for real-time processing. There's multi-level caches, there's local memory, there's significant broad range of leadership peripherals. Again, it has built-in security as well as safety features in it. Very, very powerful SoC, and that's common across all the families. And lastly, to connect up the SoC, AI engines, when the AI engine is present, the adaptable hardware engine is a proprietary NoC. The first time we've had a network on a chip, and this is to give the ultimate great performance and bandwidth and low latency across all those different engines, as well as moving on and off chip. So we're going to follow the Prime and the AI Core series with the other four series. So I'll walk through that. The Versal AI Edge is for edge and what we call endpoint applications. So these applications, for instance, in autonomous machines, cars, factories, robots, drones, some of the common attributes that they need are independent operation, very tight thermal constraints. Because they're operating dynamically, they definitely need the low latency, still they have the high performance requirements, and they definitely need security and safety built in. So this is a great series for deliver on all those applications. And of course, you can, because it's in this sort of area, you could also do massive amounts of different sensor or different real-time data feeds, process those, as well as incorporate things like machine learning and so forth. Now, at the other end of the spectrum, there's the Premium series and the HBM. Now, these are optimized for the highest, most demanding bandwidth and processing capability. So we're talking about multi-terabit bandwidth, either to the memory in terms of HBM or in terms of just, say, optical devices. So these are really for the high-end applications that you see in, say, wired communications, data center, high-end of aerospace and defense, and also high-end specialty testing, as well as prototyping. And developers could take advantage of this over 8 times the amount of still programmable but hard fixed infrastructure compared to today's leading FPGAs. And once again, they can integrate machine learning of multiple levels. And then finally, we have the AI RF series. And this integrates, in addition to all the capability we talked about, the AI engine, SoC, and so forth, integrates really high-performance ADCs and DACs monolithically. Right? This isn't an in-package integration. And this, of course, is targeted for applications like 5G wireless infrastructure, any kind of radio technology with massive MIMO, active antenna arrays, DOCSIS cable. So customers can implement not only all the radio functions like DPD, right, and other radio processing, but you could actually integrate in it machine learning, all in a single platform, a single chip. And as he said, as a product category, any form of ACAP should be fully supported for software developers, including those that don't have hardware design experience. So that's exactly what we're doing. So we're providing the full software stack, which again, Rajay is going to go and talk in a little more detail. But of course, our traditional hardware developers will also take advantage of all these incredibly powerful different engines. They'll also benefit from the fact that a lot of the infrastructure for the on-chip heterogeneity, if you will, is already hardened, which means that they will see improved development times as well as get to use more of the more flexible architecture completely rather than having to build up the platform architecture. Software developers are clearly enabled, and you have three different targets, if you will. You could target the SoC, you could target the adaptable hardware, you could target the AI engine, the intelligent engine that I mentioned. You could do that all from an integrated uniform IDE, right? It provides you with profiling and ways you could decide what's the best place to put what workload and make all that work underneath the hood. And we've interfaced that to, again, industry standard frameworks like Caffe, TensorFlow, and we also support higher level kinds of languages like C, C++, but we also support more for me, when I was going to school, C++ was a high-level language. Now it's old school. People are doing Python and all kinds of languages that I'm not familiar with. But we even enable data scientists because, again, we will interface to these industry standard frameworks. So we could even have data scientists target a versatile platform without previous experience. Okay, so now that I've talked about how broad and multi-market it will, and you see there's a lot of support for markets such as the communication markets, and I talked a lot about ML. What I'd like to do now is invite onto stage an innovator in communications as well as artificial intelligence, and I'd like him to share his thoughts on the challenges they face as we deploy 5G, and also the important role that, say, Versal can play in this. So please join me in welcoming Dr. Tero Risa from Nokia. Great to be here.
So I come from Nokia Mobile Networks, and we are a provider of telecommunication network, hardware and software, all the way from the antenna up to and including the cloud. So currently we are deploying the 5G. At the same time, we have to support the previous generations as they are already widely deployed. And new Gs will come, and the new generations will come, and we have to continue keeping the pace up with the increased complexity. So the complexity will grow so that we will have tens of millions of parameters to optimize, and it will be way beyond any human capabilities. So basically, machine learning is not an optional for us. We have to deploy it widely to manage the complexity in our networks. So now that we have established that machine learning is something we have to do, why not take all that it has to give to us? Why not to make best out of it? So our vision is that we will optimize every network element to its specific operational environment. So this means movement patterns of people, machines, the natural terrain, so buildings, structures, even the infrastructure itself. So basically, the system has to become aware of its environment through machine learning. What this means for us is that we have to do low latency, high efficiency inference for use cases such as anomaly detection, predictive maintenance, security and resilience, and radio resource management, as you also mentioned.
Sounds like an incredibly complex problem where you need amazing amounts of computes, but there's very low latency. You need this flexibility because it's a very dynamic environment and all these parameters you need to optimize. Can you tell a little bit more about the next level of challenges and what you were looking at to solve those?
Absolutely. So to increase the problem even further is that every single network element, when it's optimized the environment, also has its dedicated network to run. Not only the learning or training has to be done separately, but actually the topology and architecture of the network can be individual for each element. And then we have to run multiple models sharing the same hardware. And the low latency requirement means that we have to have low paths, practically paths 1, and there are no ready-made solutions for us. And this does put a lot of the burden to the software development, the platforms itself, and then the algorithmic innovation. So, as you know, Nokia has been working on this with you guys for a couple of years now, and I am really excited to see the platform to gain a wider audience today.
Yeah, and this challenge you have is tremendous, but as you said, there's no existing solutions for this. But I think this is where we can help, and we're very excited to help how you innovate and the kinds of things that you could do to realize this. So can you tell us a little bit about some of the micro-architectural requirements that you need in order to realize this with your innovative expertise in that?
Yes, and I think currently the teraops are getting way too much emphasis. So we need them. We need a few tens to hundreds of teraops of computing power per element. However, that's only part of the solution. We also have to gain high efficiency, so we need heterogeneous execution platforms. Binary networks do have their place, but they can't solve everything, and we do need to go from binary 4-bit, 6-bit, 8-bit to 16-bit integers in our execution. So what's announced today, you have exactly the traditional fabric to do the lower bit with computation, and then do the AI engine to make the heavy lifting for systolic array matrix multiplications and the traditional AI computation. However, what's even more important for us is that you have high-speed connections between the execution units and the memory elements. And in most of our use cases, when we have the teraops, the memory becomes the bottleneck. And what we really are looking forward of doing with Versal is to have custom memory architectures for our applications. And I believe that that will be the key element delivering the performance and efficiency we are looking. So I do see it as a big leap ahead for us in achieving this high efficiency, low latency inference in our systems.
Sorry, I'm really excited the fact that we think very much alike. I've also mentioned the fact that there's an over-focus on just teraops. A lot of it has to do with data movement. A lot of it has to do with the efficiency of what you can do with the algorithms and the architecture. So I'm really excited that you're taking advantage of all these features we built into the Versal architecture. Thanks so much. Look forward to continuing to collaborate together. Thank you. Give it up for Taro. Okay, so the last bit of news I want to share with you today is related to our data center strategy. In fact, we kind of foreshadowed this at our investor conference in May when we talked about that we are going to offer some boards. And the reason for this is very simple. In the data center market, traditionally we provided silicon plus software development stack. And because there are so many different types of systems we go into, we hadn't really provided real full production industry quality kind of boards for shipping. But we're changing that in the data center because in the data center there are very standard form factors, very standard interfaces. And frankly, that we could also add a lot of value to those who are developing applications targeted for the data center by quickly providing boards as opposed to developers having to wait for someone starting from chips to develop those. And for our customers that are directly purchasing these, some of them may either not have the board development expertise in-house, or they just rather focus their R&D on other ways to increase their value add and differentiation. So we are going to be introducing boards as we discussed. The first one that we're going to introduce is for compute acceleration, because remember, as I shared when I talked about our data center opportunity, it's not only in the compute area, it's storage and networking. But this first board that we're introducing has to do with compute acceleration, so fit into PCIe standard form factors as other accelerator. But this is not just like any other accelerator card. Again, remember, because of its adaptability, it can be optimized as though it were custom silicon for just a very broad range of applications, including, but not limited to machine learning, including applications that have integrated machine learning. And it can be used with lots of different data center architectures in mind. In fact, the data center architecture itself is being disrupted. So it could be used as a standalone kind of dedicated appliance, if you will. Personally, I think one of the more compelling data center models is deploying very broadly these very adaptable accelerated cards, and then deploying or allocating from this pool of physical accelerated cards, however many resources you need for the active set of workloads that are running in the data center at that moment, and then having DSAs, overlaid to do the optimization on those cards. So this gives you the highest throughput in your data center for the workloads that are happening. And as workloads evolve over time and say the balance of the workload, by the way, this is true for either public cloud or on-prem, you can get the maximum performance throughput as well as reducing your TCO. So all this is conceptual, which is great, but I just want to show you we got something real here. So Hector is going to give me something I'd like to share with you. Thank you so much, Hector. Appreciate it. So, I would have stuck it in my pocket, but it doesn't quite fit in the pocket, so. All right, and this beautiful, lint-free wrap. So, here we go. All right, meet Alveo. As you see, very standard form factor. It's complete, and this is based on our current 16 nanometer UltraScale Plus product. And again, it's not like any other accelerated cards. As I said, it's adaptable. And really that means, first, there's three big differentiators, I would say. It's obviously fast. That's the whole point. I'm talking fast, as you saw, compared to even server class CPUs, factors of 10, even up to 100. You saw the 30x improvement Twitch got. That was based on 16 nanometer technology deployed in Amazon's cloud. So the same technology. So it's really fast. And, again, it's adaptable. That means, and by the way, since we've designed all this, you don't have to worry about some of the development, but you could use this for your application. You could use this for machine learning inference, many different networks and so forth. And you could do that, and you can change whatever you want to accelerate on this card. And the third differentiation is by doing this, as I said, we've made this platform, the power of adaptable platforms, much more accessible, right? We did the work of creating this shell, obviously designing the board, the firmware, the software, everything, right? So we removed all that extra effort. It also enables you to leverage what might be in the cloud and then use this for on-prem deployments. And we're working with ecosystems, which I'll talk about in a moment, to sort of make that even more seamless. So bottom line is this gives you the power of leading edge adaptable acceleration without all the work and effort, and it's very accessible. And we'll be shipping this at the end of this month. Okay, so by the way, so you'll see Alveo demos with some of the partners. Later we have an Alveo developer zone, ecosystem zone, and so please take a look at that. So I kind of alluded to this, so I want to talk about this more, is like one of the key aspects of our Alveo launch today is the fact that we've also been enabling an ecosystem. And this is really important. It's an array of applications that range from database, data analytics acceleration, image and video processing, financial services, and of course, machine learning. So we have 14 of those partners, again, in the Alveo ecosystem zone that's going to be displayed here in the afternoon. But we're not just stopping at those types of ecosystem partners. We're also working with the key top leading OEMs like Dell, HPE, Fujitsu, and IBM to help enable the customers they support, critical customers they support, to have Alveo work with their really popular server SKUs so that we can empower those customers that really want to get this kind of capability but work through their trusted OEM partners. So we're also working with system OEMs. Okay, so please have a look. We're really excited. I'm going to hand this back to Hector. Thank you so much. All right. So the last thing I want to talk about is, so we have this ecosystem that we're working with and driving, but we also work with a fairly small set of silicon partners. And one of the partners over the last few years that's been very important to us, and we've had a very fruitful relationship, is AMD. I think AMD doesn't really need any kind of introduction. The only company that provides both server class and client CPUs, as well as a broad portfolio of GPUs. And what you might not know is that we've been working together with AMD in a number of technology areas, including C6, which stands for Cache Coherent Interconnect for Accelerators. This is a standard that enables CPUs and accelerators like FPGAs or GPUs, and in the future ACAP, to operate as peers in a system through a very high bandwidth, low latency interconnect, and even with shared memory. So we work together with AMD as well as multiple other key silicon leaders to develop that standard. More recently, what we've been doing is our teams have been working to harness the power of some of their leading edge recent products, like the EPYC server, together with some of our leading edge products to demonstrate the kind of leadership performance you can get in a data center by using the strengths of both. So to help me share some of the common vision that Xilinx and AMD have together in terms of the direction of the data center, as well as to talk about some of the fruits of the partnership I just described, I'd like to invite Mark Papermaster, the CTO and Senior Vice President of Engineering at AMD, to join me on stage here. So please give me a good hand.
Hi, Victor.
Welcome. Good to see you.
Good to
Thanks
see
for
you.
coming. Yeah, thank you. So, I already talked about how, we've, good to know that there's hard news to show, but hopefully there's no speed readers out there. So look, I kind of said in the introduction that we actually share a lot of common vision about where things are heading in the data center.
We do.
We talked about our collaboration on C6. And so maybe you can share your thoughts on the direction of computing in the data center, as well as what we did with C6 and what we're doing now in terms of our shared products, which I flashed up unintentionally.
Great. Well, I'd love to. I mean, Victor, you and I have been talking for years about where computing is going and with this inexorable demand for more and more computing. And what I love is that I think we both saw what was coming. Moore's Law was slowing down. It's not that we're not getting better semiconductor nodes every generation, but we're not getting the frequency increase that we used to. The costs are going up, and the workloads, meanwhile, aren't slowing down at all, right? They need more computation and different types of computation, and that's what's really led us, I think, to align on this need for a heterogeneous platform. So I think that's really been exciting, and it has led to our collaboration in the industry on C6. So how do we even connect devices better moving forward to enable more and more performance, satisfy those customer needs? Absolutely.
It's all about system performance. And
it is.
I think that's what we see, and we also see that the need for this partnership in terms of a real ecosystem for the betterment of our customers. So how about talking a little bit about EPYC and some of the really great features in EPYC and how our leadership products can work together?
Absolutely. Well, our vision in creating EPYC and creating the new Zen core that powers it was to bring AMD back to high-performance x86 computing, but more than that, with EPYC, to create a platform for high performance. One that where there was a scalar workload that could leverage the CPU in itself, it'd do very fine. But again, these new workloads, it's not just about the CPU, it's about the system. And so we designed 128 PCIe lanes that can feed into the configuration around EPYC. We designed in 8 channels of memory per socket, so you can efficiently feed those compute infrastructures. And what we did to make it even more amenable to attach accelerators like Xilinx and Alveo that we just saw, was we designed the interconnect to be glueless. So you can direct connect a Xilinx or other accelerators without a need for any chipset in between. So it really was about that vision, about making it easy to have acceleration for these emerging workloads. And again, I think working together with the Xilinx team, we really appreciate it because we've been able to really optimize the performance, tuning the drivers, turning the applications so that AMD and Xilinx work seamlessly together.
Yeah, and we're really excited to see that architecture because it really can highlight some things, and just to echo everything you said, the incredible amounts of data that people have to process. And in the data center, of course, the economics are such that you're trying to get the highest throughput and you're trying to get density of computes, right? And so all those PCI channels, that huge bandwidth and memory, and that enables us to put many of our very powerful, adaptable Alveo accelerators together. So with that, why don't we see what our teams have managed to put together? There you have it. So we focus in this case on machine learning inference. And you can see an EPYC server class product in a 4U form factor. There are 8 Alveo acceleration cards, U250 cards in there, and we've delivered 30,000 images per second throughput. Batch size of 1, so extremely low latency on GoogleNet. This is an incredible density of compute. And again, this is machine learning. You could turn this around and run other workloads, multiple workloads on each of the different accelerators, taking advantage of this incredible bandwidth, number of PCI channels, and the density and the ratio of acceleration and processors. So really excited about this machine that really warms my heart. Again, you're going to see that machine out in the ecosystem zone. But Mark, I really look forward to more collaborations like this. I know that we might have some other tricks on the sleeves in the future beyond what we're doing here. And it's really exciting to collaborate, and I think there's more good things to come. So
there is. Congratulations, first of all, on a world record inference performance. That's simply fantastic. And we do indeed look forward to providing, we have an incredibly strong roadmap of leadership CPU performance, and we're committed to expand our ecosystem for acceleration and continue our strong partnership with Xilinx. Victor, thanks very much.
Great having you. Thanks, Mark. Mark, Papermaster. Okay, so I started out the whole talk about transformation and transformational journeys. And I think we really are living in a very exciting time because the world is transforming. We've talked about it for decades, but we're really making it happen. We have smart homes, we have smart factories and offices, our vehicles are already intelligent, and they're going to become more intelligent. Industries are being disruptive, and everybody has to innovate at an exponential pace. But the opportunities are just massive, right? The opportunities for you in this room, for Xilinx and our partners, it's just massive. So we're committed to transforming. As I said, we've moved to platforms. And now, with the introduction of the 7-nanometer Versal ACAP, the industry's first ACAP, we're just raising the game in how powerful, the most powerful adaptable platform the industry's ever seen. We'll be delivering that next year. Tape-out is happening later this year. And then I also introduced Alveo, so that's even more near term. And later this month, we'll be shipping that based on our current leadership 16-nanometer FPGA acceleration. And you just saw that we were able to demonstrate industry-leading machine learning inference on that platform with a tremendous amount of compute capability in a single box. So I'd like to thank you all for coming to XDF this year to learn about our platform and understand how you can create powerful products and applications to take advantage of the power of our current products and our future products with ACAP. And I just want to say that on a personal note, again, the journey with Xilinx has been amazing. I consider myself an incredibly fortunate person to be able to lead this great company at this incredibly interesting time in the industry. I'm so excited, and the whole Xilinx team is passionate, absolutely passionate about this mission of building the adaptable, intelligent world. And I hope I've sparked a little bit of interest in you in joining us on this amazing journey. So I hope you enjoy the rest of the conference. Stay tuned. Thank you very much, everyone. Thank you.
Ladies and gentlemen, please welcome Xilinx Executive Vice President, Software and IP Products, Salil Raje.
Good morning. and welcome developers. For the past 10 plus years, I've had the pleasure and the honor to be leading the software and IP team at Xilinx. Now, what is amazing to me is the makeup of this audience today. When I first joined Xilinx, most of our users were either RTL developers or embedded software developers. But just in the past few years, we've seen incredible demand from application developers, cloud users, and even data scientists. Now, because of this demand, Xilinx has invested tremendously in the software organization. We're doing a lot in software. The challenge for my team is to do this entire software stack, starting with RTL design flows with Vivado, going to software development flows with SDX, going all the way up to frameworks-based flows, frameworks, standard frameworks such as Caffe, TensorFlow, and MXNet for data scientists. Our goal is to ensure that each one of you has a natural and productive on-ramp onto our very powerful devices. Victor talked about Versal today. Versal is super exciting for me. It is the first family of devices that has been designed from ground up for AI and software programmability. So now we can build upon this very powerful platform. I believe that Versal and ACAP is going to change the face of AI. I also do believe that we are at an incredible inflection point. Tools, IP, and silicon are coming together to make AI feasible in cloud, edge, and the endpoint. So today I'm going to give you an overview of AI, talk a little bit about some of the challenges in AI, and then talk about how Xilinx overcomes these challenges. So most of you probably know this, but AI has two distinct phases: training and inference. In training, a data scientist takes lots of data and sends them through the model. The model is fine-tuned and refined. Now, in this example, the training data set consists of images of dogs and cats. You send it through, training is iterative, has a feedback. At the end of it, you produce results. You try and reduce errors. Errors such as detecting cats instead of dogs. Now, because training uses lots of data, lots of sample set of data, and very iterative, training performance is extremely critical. Now, latency and power is not as important in training because a lot of times training happens offline. Now, once you have the trained model, you deploy the trained model in your application, either on the cloud or the edge or the endpoint. In inference, you take small amounts of data, maybe a single image, and you send it through, and you get an inferred output. Now, performance is also very important in inference, but latency is critical. And sometimes latency is actually a constraint. A lot of these applications are in real-time systems where response times matter. In inference, power is also very important. These could be deployed in edge devices where they are battery operated. But even in the cloud, power is extremely critical because you could have many concurrent inference engines working in parallel, consuming kilowatts to megawatts of power. Now, you may already know all of this, but the key takeaway is that the requirements for training are not the same as requirements for inference. You can't take the solutions in training and then move it to inference. Well, but the world has focused mostly on training for the last few years. And the world has focused on training because we were inventing AI models, and we are inventing the applications where AI could be used. But going forward, the growth is in inference. because all these AI models have to be deployed now in these applications, either in the cloud or on the edge. And Xilinx is focused on inference. Now let's take a look at some of the challenges associated with inference. Well, the first challenge has to do with the fact that the AI is getting innovated at a rapid pace. And keeping up with machine learning or AI is like shooting at a moving target. The second challenge has to do with the fact that we want low latency and high performance for many of the applications. The third has to do with power efficiency, not just in edge, but also in cloud. And last but not the least, and Victor talked about that, you need the whole application acceleration, not just your inference engine. You need to accelerate the entire pipeline of functions associated with machine learning. Now, let's take a closer look at some of these challenges and see how Xilinx addresses these challenges. A few years ago, most of machine learning was focused on image classification and maybe recommendation engines. But just in the past few years, there's been a tremendous growth in the universe of applications where machine learning can be used. Object detection, segmentation, speech recognition, anomaly detection are just some of the applications where machine learning is being used. And there are many, many, many more. The universe of these applications is growing at a tremendous pace. Now, if you just look at any one of these, there's a lot of innovation going on in AI models also. Every day there are new models being created to be used in any one of these applications. Now, if we take a look at just one of them, classification, image classification. Now, image classification has been around for 30 years. But AlexNet came out in 2012, and since then, in the past 6 years, there has been a tremendous growth in the number of models being created. There has been an explosion. For the first few years in this period, the focus was on improving accuracy. But you can see lately, you can look at the example of MobileNet, the focus is on improving the efficiency of the AI model. The reason they are focused on efficiency of the AI model is because this AI model can now be deployed in mobile devices. Now let's take a look at the structure of these AI models. Well, if you look at the structure of these AI models, they started with very simple feed-forward networks where convolutional layers talk to the next layer. Very simple AlexNet. Now we moved on to more complex networks where there are many convergences and divergences, such as GoogleNet. Moving on to even more complex networks, there are convergences, divergences, but there are also bypasses. This is DenseNet. Now there's also research today going on with respect to doing some of this work through shifters, not even using matrix convolutions. To me, if you look at these networks, look at these models, there's really no commonality between these networks other than the fact that there is some linear algebra going on in the background. They are very diverse. Not a lot of commonality, and the diversity will only increase. Now you overlay this with the fact that there is research going on and there's deployment of low precision arithmetic. We started in 2012 with floating point 32. We are now at integer 8 arithmetic, moving to binary networks potentially by year 2020. Now the reason is very simple. If you look at the energy consumed by floating point 32-bit adds, it is 30x compared to integer 8 add. And that's why people are moving towards lower precision arithmetic. Now, with all this innovation in AI, imagine, if you will, you're creating a fixed function chip, fixed architecture ASIC, to accelerate one of these inference engines. You start off with a spec on your most state-of-the-art model. After a few years, you get the silicon back, the state of the art has changed. Now your silicon is optimized for a network that is not state of the art anymore. Fixed silicon architectures are not the answer. Answer is adaptable hardware. Adaptable hardwares such as Xilinx FPGAs and ACAB allow you to customize your data flow. They customize your data flow towards your current state-of-the-art network. They allow you to customize your memory hierarchy. You can try and increase the amount of on-chip memory used instead of going to DDR. You can customize even the precision. You can even have mixed precision. And you can do all of this, and when the state-of-the-art changes, you can re-implement all of this without a silicon rev. Now, Xilinx and others have created something called domain-specific architectures. Victor talked about it. DSAs, domain-specific architectures. These can be created and tuned for a class of networks. Tuned for a class of the current state-of-the-art networks. And these optimize across these vectors. Custom data flow, custom memory hierarchy, and custom precision. You can customize all of this to improve your latency, improve your power, improve your cost, improve your efficiency. Now, one such pioneer in creating DSAs has been DeFi. DeFi has unique pruning technology that allows you to customize the data flow. They can customize the data flow for the networks in question. They can even quantize your network, tune in the precision. You can retrain and get the accuracy back. Their technology was so unique, we started working with them about 2 years ago. We partnered with them. Fantastic partnership, great technology, and now Xilinx has acquired DeFi. So all of DeFi technology is now available to all our users. Now this is an example of a DSA that DeFi has created. This is focused on speech recognition, tuned towards LSTM networks, long short-term memory. They made sure that they customize the memory hierarchy using sparse matrix computation. So you can improve power as well as cost. And look at the precision. 12-bit weights, 16-bit activation. No fixed function chip would go for something like that. Right? Tuned in the precision to improve your latency, improve your power, improve your cost. Now here's another DSA that we created. I think Victor talked about it, XDNN. This was focused on a class of feed-forward image classification networks such as YOLO, ResNet, GoogleNet. We also customized the memory hierarchy here, where we added buffering between layers of convolutional layers so that we don't have to go to DDR again. Reduce the times we go to DDR to improve, again, latency, improve power. We did integer 8. Now, by itself, it was interesting. We got pretty good performance. But we actually found more innovations, more algorithmic improvements that we could do on XDNN. And within 6 to 9 months, we improved it further. And Victor talked about it. We improved the latency and got to a third of the latency that we had in a previous version. And we improved the throughput to almost 2x. And we re-implemented the whole thing, again, on the same silicon, no silicon rev required. You can continue to innovate on your networks. You can continue to create these DSAs. You can tune your DSAs to your network, re-implement it, no silicon rev required. So we talked about latency. Now let me explain why latency is important. Let's say you're driving a car Or rather, the car is driving you. In your autonomous car, you have an inference engine. The inference engine is watching all the hazards, and as the hazard approaches, the inference engine will try and stop the car. The faster the inference engine reacts, the better the latency, the lower the latency, the shorter the stopping distance. And the chances of you avoiding the hazard go up. So latency is, of course, very important. Low latency is very important. But you may be driving very fast. Therefore, frames per second is also important. Throughput is also very important. So throughput and latency is important. Low latency is important. So let's look at how GPUs and CPUs handle throughput. Let's see how they optimize throughput and contrast it with how FPGAs and ACAPs optimize throughput. So with GPUs and CPUs, you have to load in sets of data. They call this technique batching. Load in inputs together. At this point, you load in the model weights. Now you compute your results and outcome results together. Now, the reason you have to load in model weights together to compute at the same time multiple results is because memory is a bottleneck in these instances, and you don't want to be loading weights again and again. Now, because you do this type of batching, you can get either high throughput or low latency, but not both at the same time. Well, let's look at how FPGAs handle throughput. Well, FPGAs, you can actually pipeline the input, get the results out. Pipeline it, get the results out. You don't have to wait for all the inputs to be loaded together. So you get low latency. Now, the way FPGAs and ACAPs would handle throughput is by customizing again the data flow, customizing the precision, customizing the memory hierarchy. So what you get here is high throughput and low latency. Let me show you a benchmark example to illustrate this point, high throughput, low latency. This is a Versal device benchmarked against GPUs and CPUs. In this scenario, there is no latency constraint. No latency constraint. The Versal device would be 2x better than GPU and 43x better than a CPU if you use GoogleNet as your benchmark. Throughput, images per second. No peak teraop numbers here. Real numbers. You get 2x better than GPUs, 43x better than CPUs. Now let me tune in a latency constraint. Sub 7 milliseconds. At this point, Versal, interestingly, remains constant with respect to throughput. But GPUs has dropped, and now Versal is 2.5x better than a GPU, and Versal is 72x compared to a CPU. Let me tune in the constraint even more. I tighten it to sub 2 milliseconds. Extremely valid constraint for many of the applications. Now Versal is 8x better than the GPU. Well, and the CPU has dropped off the chart because it can't satisfy this constraint. Let me show you benchmark results with more GPUs and our current Alveo board and the Versal device. You can see Alveo gets about 4,000 images per second with a constraint of 2 milliseconds, and Versal gets about 22,500 images per second using GoogleNet. Significantly better than all the GPUs, even with our current board that we launched today. But that's not all. If I use D5's pruning technology, it goes better. Alveo gets to 5,300 images per second, and Versal almost touches 30,000 images per second. D5 can give you 1.3x to 8x better performance depending on the network you use. So we talked about latency. Let's talk about power. Now, it may be obvious that power is important for edge and endpoint devices, but it's also very critical for cloud. And I'm going to show that with an example from one of our customers here in the audience today. This is SK Telecom's personal assistant device. This is the device they sell in South Korea, and it's the most popular personal assistant device in South Korea. Like Alexa, this will send data up to the cloud, and SK Telecom will do automatic speech recognition. Now, SK Telecom has seen some tremendous growth with this device. Just in the last 2 years, they've gone from 0 active users to 4 million active users. And they expect that they would have to handle about 1 billion conversations every month. So naturally, they were looking for some acceleration. Now, they started doing benchmarks against GPUs, FPGAs against GPUs, and they saw that FPGAs gave them 5x better performance and latency, low latency compared to GPUs. But interestingly, they got 16x better performance per watt compared to GPUs. So they did their own DSA, optimized for their speech recognition, deployed it. The performance per watt advantage that they got translated directly into total cost of ownership because there are many inference engines running in the cloud at the same time. Now, SK Telecom, as I said, is in the audience. They have a talk today in the afternoon. So anybody wants to understand how they did it, they should attend this talk from SK Telecom. So yet another consideration has to do with the fact that inference engines don't work in isolation. They have pre-processing and post-processing functions that go along with inference engines, and Victor talked about whole application acceleration. You need to accelerate the entire pipeline of functions to get your required latency. Now I'm going to illustrate that with a real example, again from a customer. This is in the smart city space. As you know, smart cities are popping up everywhere. In smart cities, there are networks of cameras that are deployed to avoid threats. By some accounts, there will be about 1 billion cameras that will be installed on government sites and commercial buildings by the year 2020. Lots of data. Now, whether you're identifying a criminal from a crowd or identifying a stolen vehicle using license plate recognition, AI is playing a huge role in all smart city applications. Now, what I show here is the back-end engine of a smart city camera deployed in the cloud. Now here, the application has been split between CPU and an accelerator. Now in this scenario, the accelerator happens to be a GPU, which can only accelerate CNN function or your image classification function. And at this point, you get about 82 milliseconds of latency, 75 watts of power. Now, if you redo this application in an FPGA, you can move some of the functions that were surrounding these inference engines into the FPGA again. The motion analysis function was moved to FPGAs, and now you get 26.1 milliseconds of latency, 50 watts of power, and the throughput also improved 3x. It went from 12 frames per second to 38 frames per second. Again, whole application acceleration, not just the inference engine. Okay, so we talked about the importance of agility. We talked about low latency and high performance. We talked about power efficiency. We talked about whole application acceleration. But what is also, or just as important, is getting you to implement, the developers, to implement your AI function in your applications. And my team has been focused on creating the entire solution stack, the machine learning solution stack, to make your job easier. And this is a solution stack that we have developed. This is what we've assembled. The components come from us, from our partners, or some come from the AI community overall. Let's start from the top. We now have support for standard frameworks, Caffe, TensorFlow, MXNet, that allow a data scientist to create custom models. But you could create custom models, or you could use some of the models that we have created. These are pre-trained, pre-optimized models that can be deployed in your application. And we deploy them in a library that the industry calls Model Zoo. We also have accelerated libraries. These are library functions that go around inference engines that allow you to do whole application acceleration. Functions such as OpenCV in the vision space. We have pruning and compression technology that allows you to customize your data flow. We have quantization and compiler tools that allow you to customize the precision, do the retraining, and then deploy your network with no loss of accuracy. We have runtime libraries that allow your AI application to talk to the external CPU host, the x86 host, or the processing subsystem within our device. We have DSAs. You can write your own DSA for your specific application, but we have our DSAs ready to be deployed. XDNN, Descartes for speech recognition, Aristotle, this is a DSA for image classification for the edge-based devices. And this all sits on top of FPGAs, either in the cloud using Amazon F1 instance or Alibaba FPGA as a service, Huawei, Nimbix, and so on. Or they can be deployed on our Alveo boards, the ones that we launched today, or they can be deployed on custom boards that you create. We are very focused on AI and making sure that all application developers have an easy route to creating their AI applications. We are continuing to add more and more to the accelerated libraries, improving the quantization tools, compiler tools, adding to the model zoo, and so on. We'll continue to invest heavily in this space. Artificial intelligence revolution is here. There are many opportunities in inference. There are some challenges as well. We believe that our adaptable hardware is the best alternative to implement your AI application in cloud, edge, or endpoint, because we allow you to match the speed of AI innovation and not be constrained by silicon design cycles. We get you the best low latency and highest performance for many of the applications many of the demands of applications. We get you the best power efficiency, not just for edge, but also for cloud. But last but not the least, we allow you to do whole application acceleration. As I said in my opening remarks, we are at an inflection point. Tools, silicon, and IP are coming together to make your AI application feasible in the cloud or at the edge. Whether you are an AI expert or if you're starting AI for the first time, trying to understand how to deploy your machine learning AI application, we look forward to working with you on your next project. Thank you.